Good afternoon. Sorry about that. Everybody is waiting for their coffee? Yeah? Okay. So my name is Vijay Bolloju. I am a Director of R&D at IVP Semiconductor. So today I will talk about something a little bit different. This is about power electronics, right? Most of us always talk about the ICs and AI and ML and all the stuff, right? So power is very important, especially now with electric vehicles, renewable energy. Power electronics is becoming very, very critical technology for us, right? So as you can see, there is a strong market demand for power electronics. IVP is a fabulous power semiconductor company. We are working on solutions for upcoming applications like EVs and renewable energy, efficient appliances, right? So fortunately or unfortunately, we inherited a very low voltage platform for electric vehicles, right? 48 volts. But we want bigger and bigger electric motors, like 10 kilowatt and up. So what it does is it pushes your currents very high. So in India, if you look at how people design power electronics, they tend to put all the MOSFETs, IGBTs on a printed circuit board. Printed circuit board, as you know, is a very bad thermal medium. Delivering such high currents is a challenge. So we basically wanted to work on these integrated power modules, which can deliver high currents at very, very efficient form factors, right? So if you look at the electric vehicles, actually the systems used in electric vehicles are much more demanding than the systems used in space. Because as you know, when you drive in Bangalore kind of roads, you have potholes, you have flood waters, all kind of 3 people, 4 people riding on the bike, right? So that puts a lot of demands on the electronics. For example, these are some of the key requirements. You need to be high reliability. If you buy a vehicle, you want it to last 5, 10 years, right? It has to be lightweight. The electronics have to be lightweight to get a longer range for the battery. And then it has to be compact. It has to fit into the vehicle with ease. And IP67 or better packaging, right? So that when there is flood waters or you wash the vehicle with high pressure jets, it should not get damaged. Then a high performance so that you get the longer battery range, right? And of course, it has to be economical. India can be described as a country who asked, "Kitna deta hai," right? You need to answer that question so that you will be able to sell your products. Characteristics are high operating temperatures. As you know, ambient temperatures are going up. So it has to work at 70 degrees plus environment. High currents, like I said, because of the low battery voltage, the currents are very high, touching almost 500-600 amps, right? And the nature of the loads are like short peak loads, which are actually more strenuous on the electronics than continuous high temperatures. I will talk about it a little bit later. Cyclic operation. As you know, when you drive in Bangalore-like cities, you are going stop and go, right? That is actually much more severe on the electronics than actually driving at 100 kmph on the highways, right? Subject to shock vibrations, subjected to high pressure water jets and salt sprays, right? So if you open any EV electronics, this is what normally you find, right? So a lot of MOSFETs or devices parallel on the printed circuit board. They have to do that because printed circuit board is not a good thermal conductor. So you get very little from the device when you put it on the printed circuit board. For example, you put a 300 ampere device on a printed circuit board, you probably get 30 amperes out of it. So 1/10 of the current. That means you need to parallel multiple devices to get the current you need. Also, you look at these through-hole components. You can see how many screws are there. Each screw means a second or two to assemble. So your throughput of the assembly will reduce, and the cost of the products will go up, right? Also, PCB traces, 75 micron, 100 micron traces cannot handle hundreds of amperes. So there is a chance of early failures, right? So you can see this is a BMS board. Typically, each MOSFET costs about $1. There are 20 MOSFETs. So the $20 went into the MOSFETs itself. So the rest of the BMS with all the sophisticated controllers and all cost half as much. So this is not a very sustainable design, right? So then you have integrated modules that you can buy from Europe or Korea. They use basically ceramic substrates, which are 100 times better thermal conductivity than PCB, but they're also very expensive. They're not locally available, right? And then basically use the chips to integrate onto the substrate, right? So this is basically we have a patented way to create these modules locally using highly local content. So the key to power electronic design is not electronics. If you all think it is, 80% of the effort goes into actually mechanical design, right? So there's a lot of mechanical design innovations needs to happen in high power electronics packages, right? So basically this module is created without using any substrates, without mounting the devices on the printed circuit boards. So a 300 ampere MOSFET, we can actually extract up to 200 amperes in this package. That means we can reduce the number of devices, reduce the cost, reduce the weight and size of the system, right? So a lot of the components we actually develop local suppliers, so it is very sustainable, right? So in this module, we have about 85 components integrated. If you are designing a traction system for EV, it's like a Lego block for you. You can just create your traction inverter solutions without having very knowledgeable power electronic resources, right? So if you look at BMS boards today, up to about 100 amperes, they can basically design the switch on the PCB. After that, they use a mechanical relay. So mechanical relays, a lot of companies are display. You pick it up, relay 200 amperes, it almost weighs half a kilo, right? And they only last about 10,000 cycles. In a Bangalore-like city, when you drive in such traffic conditions, so the relay life is very short, right? So now we created a solid-state relay using the high thermal efficiency circuit. So we can get a very compact, long-lasting product. Because it's being a solid state, we can test it up to 1 million cycles. That means each solid-state relay is equal to 1,000 mechanical relays in terms of lifetime, right? So if you look at the characteristics of the relays, this relay has about 20,000 cycles, right? That means on-offs. Whenever you key in your bike, one cycle is done, right? So my solid-state relays, we can get more than million cycles, right? The key is in the thermal stack. When you design very high power, high current electronics, it's not so much about the device technology, but it's about the low tech of thermal stack. So there are a lot of study needs to happen and development needs to happen to increase the power density of high power electronic systems along with the device technologies like silicon carbide and gallium nitride, right? So we basically focusing a lot on the materials. A lot of the material suppliers are available around Bangalore, but they are all like not very well known, right? So, like I said, the load is cyclic, right? when you have a cyclic load, you need to have both thermal resistance as well as a good thermal capacitance so that you will reduce the ripple temperature. So for example, you're doing a start-stop in the traffic, your device temperature is going up and down like that, right? That is very damaging to the device than basically running at a constant high temperature. That's because if you look at the thermal stack, there are different material layers which has different thermal coefficient expansion. So they have a relative expansion contraction between the layers which causes the fatigue and reduces the lifetime of the products. So if you're designing power electronics, high power electronics for your EVs and solars and all the stuff, so this is a very critical aspect of the product design. So you need more mechanical engineers than electrical engineers actually to design such high power systems. So basically you need to incorporate a lot of thermal capacitance to reduce the peak ripple. The thumb rule says if you reduce the peak to average temperature by 10 degrees, you can actually extend your product life by 100%. So that's a very, very critical aspect of the high power electronics design, right? So we have a whole bunch of modules in the pipeline for various applications, right? So you can see the application space is endless. We are becoming more and more power hungry, so we want more and more power from our systems. So it becomes very critical that you pay attention to the packaging as much as you pay attention to your device technologies, right? So these are key takeaways. As you look at the costs of the devices, silicon carbide, gallium nitride, they are much more expensive than silicon devices. If you want to use those technologies, you need to optimize your device utilization through thermal circuit or packaging, right? So if you are designing for moving platforms, like any vehicle or any farm equipment, you need to reduce the size, weight of the system so that you can extend the battery life, right? And packaging improves the reliability because it is more consistent. You reduce the delta TJ excursions, so it will improve the reliability and also the ruggedness, right? That's all I have. Any questions? I'll be glad to answer.